Okay, good afternoon, everyone. My name is Keith Farrell, and I'm going to spend the next few minutes talking to you about my recently completed Masters in Building Performance entitled A Life Cycle Assessment and Comparison of Refurbishment and New Build of Concrete Framed Office Buildings in an Irish Context. I always need to take a bit of air after I've said that. It's a bit of a mouthful. So just very briefly before I get into the thesis, I'm just going to give you a quick overview of my background, the journey to the Masters, which I think is very important. The field of study for the Masters and how I got there, it's embodied carbon life cycle assessments in office buildings, and I'll go through the methodology and the case study, and finally I'll bring you through the results and conclusions. So I qualified as an architect from UCD in 1997, and I spent the next 9 years in an architectural practice in Dublin, where I worked predominantly on a number of residential projects, including my own house. In 2006, I joined ESB International as a senior architect, got the opportunity to design and deliver a number of commercial projects like this ESB Networks depot in Letterkenny. That's about as far as my international travel got. In 2012 then, a slight change took me into a role in facilities management in ESB. The role started with delivery of several small-scale projects like canteen, roof and window upgrades. And by 2015, the role developed into a delivery of larger projects that included whole building refurbishments. And in 2015, I got to deliver my first whole building deep retrofit. So it was this retrofit in 2015 that opened my eyes to how much I didn't know about energy retrofit and the whole area of energy efficiency design. So I had a huge reliance on suppliers, contractors, and M&E consultants. So it was around this time that a colleague made me aware of courses being provided in TU Dublin, then DIT, in the area of NSEP. So I applied for the men's course in 2016 and was unsuccessful due to the limited number of places. So that was giving me an indication I was going in the right direction. But I was successful in my application for the postgraduate certificate in building performance in 2017 and commenced in 2018. So the course was excellent, where I completed projects on deep PHPV, hygrothermal risk assessments, linear thermal bridge, cost optimality, and it provided a strong foundation in the principles of energy efficient design. So I continued on to the second year, the postgraduate diploma, where the focus changed from domestic residential to multi-unit residential and commercial, and exposure to more complex tools like SBEM and Design Builder. And it was during one of these projects that, while assessing the most suitable materials for an energy retrofit in a historic building in central Dublin, that I was introduced to the whole area of embodied carbon. So this provided me with the inspiration to continue to the Masters and sowed the seed for my Master's subject. So at this point, I just wanted to give a broad definition of embodied carbon. So I've broken this up just into talking about embodied carbon in 4 particular pieces. Emissions associated with all the activities of procuring, mining, harvesting raw materials, transforming these into materials into construction projects, transporting them to site, and incorporating them into a building. So I'm going to call this stage A. So if I'll just take a simple example of floorboards. We cut down the tree, put the log in a truck, we transport it to a sawmill. There's emissions going on to take it there. We have machines in there. We need to debark the log, cut it into rough planks, plane and profile, send it to a kiln, put back on a truck, and then send it to site. We're ready to fix. So we've gone through the first part of the embodied carbon. Then next, the plank is in the in-use stage in the building. So over its life cycle in that building, it might have to be planes down a number of times and resealed. So it's all the emissions to do with this. And then we're at the next stage, which is the disposing at the end of life, and then any emissions to do with recycling. So just thought it was good to kind of recap on that. And then just one other thing, I suppose for me, as I was going through this, it's just a note on CO2 equivalent. So when we talk about emissions, we often refer to carbon. It's a buzzword. During the Masters, I found myself getting quite jargonistic with things. So when we talk about carbon, we generally refer to a number of emissions, not just CO2 associated with a product over its life. And so to simplify things, we use what's called CO2 equivalent. And this is the number of kilograms of CO2 emissions with the same global warming potential as 1 kilogram of another greenhouse gas. So just as an example, CO2 is a global warming potential of 1, so 1 kilogram of CO2 is equal to 1 kilogram of CO2 equivalent. Methane, on the other hand, is a global warming potential of 25, so 1 kilogram of CH4 is equal to 25 kilograms. So at any stage in a process, if we've 1 kilogram of CO2 and 1 kilogram of methane, we've got 26 kilograms of CO2 equivalent. So when I start talking about carbon later on, this is an important thing to understand. So the master's started in earnest in January 2021, where literary review and background research into my areas of interest, embodied energy, offices and refurbishment, provided the foundation for the research thesis. 85% of buildings in use in Europe in 2050 are already in use today. And it's clear from this that the existing building stock will play a clear role in contributing to emissions over the next 30 years and beyond. But they also represent an opportunity to positively affect emissions if they can be upgraded to improve their efficiency. Ireland's renovation strategy, also published in 2014, places an emphasis on consideration of existing buildings in achieving Ireland's 2030 and 2050 emission targets. In Ireland, like many other European countries, our energy regulations focus on operational carbon only. That is the amount of carbon emitted to run a building once it's in use. We do not consider the embodied carbon. So remember the definition. We strive for building energy ratings of A in our new builds and B in our refurbished buildings. But the records show that only 3% of registered BER ratings for commercial buildings lie in the band from B1 to A1. So we have a large number of commercial buildings that do not make these standards. In terms of building numbers, Ireland has an excess of 42,000 offices. And of these, 40,000 are described as small or less than 1,000 square metres. So at this point in the master's, I decided to focus in on these small commercial buildings. The need to address the energy efficiency of these poorly performing offices is clear, but with so many, what level of refurbishment makes sense to affect overall emission targets? Are they worth renovating at all, or should we just demolish, get rid of these poor performers and rebuild new to current standards? So to attempt to answer this question, my research was indicating that a more holistic approach to environmental assessment of building and their emissions was required. An approach that does not simply measure performance of operational carbon. Also at the same time, finding through the research that a number of countries in Europe are moving towards adoption of lifecycle assessment, LCA, in the construction industry to assess building impacts. So what is lifecycle assessment, or LCA? It's a methodology for assessing environmental impacts associated with all the stages of the life cycle of a commercial product, process or service, in this case, buildings. For building assessments, there's a clear framework defined in EN 15978, can be summarised in the following table. Breaks the life cycle assessment into 4 distinct stages and sub-stages within these. We also hear many phrases associated with LCA. I just want to draw your attention to some of these, as they'll appear in a few minutes when I'm talking about the results and analysis. So firstly, upfront carbon. This is the emissions associated with the initial part of the building process, getting all the materials out of the ground into processing plants, creating products, getting to site and putting in place to provide the finished building. Next, the embodied carbon, taking account of the upfront carbon, but also including the replacement cycle and the end of life cycle. It excludes operational carbon. And finally, the whole life carbon, all the emissions from the embodied and operational carbon. I just want to touch on how life cycle assessment is completed and the information required to carry one out, as it was key in my study. I used one-click LCA to carry out the LCA for the masters. So the software requires a number of inputs. Project information, it's information about the building. So is it a new build, a refurbishment, frame type, and the element inclusion. So it starts at the foundations and works its way up through the substructure, the superstructure, the finishes, the external areas and the services. The building materials, I'm going to come back to that in a second, just go into a little more detail. Annual water and energy consumption, construction site operations, building area, and the calculation period. The calculation period is typically 60 years. So just back to the building materials. So this is the most intensive part of the LCA. It requires the establishment of a full list of everything that goes into the building and the quantities of each item. So this is referred to as the LCI, the life cycle inventory. Each element then is linked to an environmental products declaration, EPD. This gives all the relevant information on the various emissions from the product. So a typical product selection in the LCA software looks something like this, and it gives, so starting at the bottom then, it will give you the EPD, it will give you a description, the quantity of the material, the unit of the material. And this can be anything. This could be meters, meters squared, meters cubed, liters. So, you know, you make an error in this in your calculations, and it can send you wildly off in the wrong direction for weeks, as I found. Material description, and most importantly, probably, is the emissions. So in this case, we can see that the phenolic insulation is given, you know, it's a small little innocuous little kind of green figure, but it's 2.4 tons for the emissions over 60 years in this example. So, so the software goes through all these items and then it outputs total lifetime emissions. That's just a quick visit into how the LCA works. So EN 15978 looks like a clear framework that I can use to assess the emissions in new builds and refurbishments over a 60-year life cycle and then compare and analyze. But in comparing a number of studies that I had reviewed, I discovered that the methodology was being used in a piecemeal and somewhat subjective way. So on comparison of a number of studies, I discovered that very few studies were carrying out LCA investigations using the whole framework. So as I delved further into why, I discovered that a lack of information from manufacturers in the form of EPDs, scant information on M&E systems, and focus on part of the life cycle were the main reasons for a lack of complete LCAs. So at this stage, I was slightly concerned that I wasn't going to be able to complete a full, proper analysis of the buildings. So as I continued my research, I found that there were several guidance documents on LCA had been recently published to help provide a more robust approach to using EN 15978. One of the clearest from an Irish perspective was the Royal Institute of Chartered Surveyors, RICS, in the UK. Their document entitled Whole Life Carbon Assessment for the Built Environment. CIMSE had produced TM65, Embodied Carbon in Building Services, calculation guide in 2021. I think that came out in June 2021. And yeah, that's a good read. And coupled with studies by the Carbon Leadership Forum on embodied carbon in M&E systems and tenant fit-outs, there was now a suite of guidance to be able to complete a robust whole life assessment on a building. So what I wanted to do was not leave out any parts of it, not, that we had everything assessed in there. So I turned my attention then to how to compare new builds and a refurbishment. So in order to remove the subjectivity, I wanted to compare buildings that were similar in shape, form, and materials. And what I mean by this is some of the examples I had looked at when the studies were doing comparisons, they were maybe comparing an existing building to a new build, which wasn't the same area, wasn't the same shape, and you really weren't getting the proper comparison. What I wanted to do was set a foundation here for comparing like with like. So I turned to my own work, where in 2016, I completed a refurb of a small concrete frame building. So using this as a base, I could use the as-built information to build an energy model which reflected the completed project, simulate a number of scenarios, including a new build scenario. So using the data from each model, I could develop an LCI for each model, and a life cycle assessment for each model could be produced, and then a comparison made and analysed. So at this point in the journey, I had got to my title, and the primary aim then was to compare a number of refurbishment scenarios of an existing office building with a new build office scenario using life cycle assessment to determine if new build or retrofit is more sustainable when considering the emissions over the building's life cycle. And though what happened to me at this stage, I just seem to get into big long sentences, especially when I'm taking on occupational hazard. The key objectives here, I wanted to complete all the stages of the LCA, assess all the material groups, use a number of metrics, whole life energy, whole life carbon, body carbon, and upfront carbon, establish patterns of influence in those stages that I talked about earlier, see if there are any materials which were more bigger contributors than others, and likewise with the systems. And then assess the impact of grid decarbonisation scenarios on operational energy emissions. I'll talk a little bit about that in a minute. So the methodology was based around two established frameworks, one for calculating operational energy, NEEP, and one for LCA, EN 15978. The case study office refurbishment was selected. Its material specifications and operational energy use were used to form a base case. So first, in order to obtain the operational energy input for the LCA, so we had to figure out what the operational energy over the building's life cycle is. An energy model was constructed in Design Builder and then validated against the actual BER certificate that we had. The operational energy values were then taken with the material specifications into the LCA software, one-click LCA, and one-click LCA is third-party verified for EN 15978, and then the LCA was calculated. So a layer of robustness was added to the methodology by applying the guidance set out in the RICS documents, the whole life carbon assessment for the built environment. So then, having established a set of results for the LCA for the case study or the base case, this base model specification was adapted and the methodology applied to achieve an LCA for two further refurbishment cases and a new build case. So there were a total of 5 cases were produced and analysed. So the cases, so this is slightly confusing, but case 2 is actually the base case. This was the refurb in 2016. A do-nothing case with no refurbishment, no replacements over its life had been included as case 1. So this was the pre-refurb case, it didn't do anything. Case 3 takes the base case, carries out some alterations to bring the scenario to major renovation scenario as per Part L. So we're really making some changes to bring it from a C1 to a B1. And then case 4 is the refurbishment with its operational energy performance brought in line with a new build scenario, so achieving an A3. And then case 5 is a new build case achieving an A3 rating. The BER specifications shown here for each of the cases. And as these specifications change, to achieve greater operational energy efficiency, the altered specifications in the materials, they're fed into the LCA through the materials inventory. So in the case of the new build, there's substantial additions as all the foundations and structural materials have to be added in. So, because we're doing a refurb of an existing building, we're not looking at the foundations, we're not looking at the slab, we're not looking at the structure because it's all there already. So we don't have to look at it. But in the new build, we get this substantial amount of additional material which is going into it. So having carried out the LCA for the cases, the outputs were summarised into results. Getting close now. So in relation to the primary question, the results for the life cycle energy and whole life carbon indicate that the more efficient A3 cases perform best. The refurbishment case, case 4, is the better performing of the two, just about. And this is attributed to its lower embodied carbon requirement, mainly due to the structure of frame, floors and roof already being in place. And the whole life carbon comparison has a similar result to the life cycle energy comparison. And just like we're talking about telephone numbers here when we're talking about the figures. So you can see the life cycle energy comparison in megajoules. We're into hundreds of millions of megajoules over the 60 years. And then with the whole life carbon, we're into tens of millions of kilograms of CO2 equivalent. When upfront and embodied carbon are assessed, the refurbishment scenarios perform best, again attributable to the non-requirement of the main structural items. So we can see the new build, the emissions are far greater in these initial stages because there's more materials going into the building. Having established an answer to the main question, the analysis of the results focused on the key stage drivers in each scenario. There was no surprise that the B6 stage, the operational energy, was the key driver. However, when we removed the B6 stage, the results show that the replacement and maintenance stage was on a par with the upfront carbon stage. There's a lot of talk about upfront carbon at the moment. So I'm just in the middle here. I've just gone back to the table I showed you earlier. It's an extract from the studies I reviewed, where this stage, the operational stage, has been excluded in a number of studies. So it's just reinforcing that this is quite an important stage, particularly in the office typology. Looking at the most contributing materials, we can start to see the value of the existing building emerging. what we get by reusing is saving in the emissions from the provision of the frame, structure, and floors, as mentioned earlier. So this big green bar here, the first one, is the concrete. So you can see the green represents the new build case, the yellow represents the refurbishment case to A3. Again, you can see the emissions on the concrete alone. So in terms of both scenarios, interestingly enough, the loose furniture has a substantial impact. So when I group together all the loose furniture items, it's coming out the third most impactful area when all furniture is taken together. And this is not often included in a lot of the studies I looked at, so it is an important piece. The mechanical, electrical, and plumbing whole life carbon of the A3 refurb is the highest, and that's due to there's a large amount of PV in that case on the roof to bring it up to an A3. And then lastly, a number of grid decarbonisation scenarios were applied to the cases. This was carried out as a number of academic papers concluded that future studies should include it. And this is great, as I'm reading through these papers and they're all saying, yeah, people should look at decarbonisation. They haven't done it themselves. And so I had to delve into this a bit. And that was a bit scary, but also the RICS guidance document says that we should be looking at this as one of the scenarios when we're doing LCA. So there has been serious inroads into the decarbonisation in the last 2 decades. The emissions associated with the grid are reduced from 636 grams of CO2 equivalent per kilowatt hour to 324 grams. And this is projected to continue to fall. And that's where we're going. We're all trying to get this down. So the scenarios we looked at were taken from an air grid study, Tomorrow Energy Scenarios, and the results are shown in graphic form here. So the scenarios, they didn't affect the relative outcome of the study about new builds, refurbishments, but the decrease in operational carbon is substantial. And what happens here is that when we look at the ratio of operational carbon to embodied carbon, if we did an LCA now, you'd probably find about 80% of that carbon is operational carbon. But as the grid starts to decarbonize and go down and go down and go down, that operational carbon, that ratio is going to come down. So potentially we could be looking at in 10 or 15 years time, if the grid starts to come down and we've less carbon coming from operational energy, we will be honing in on embodied carbon in materials. So that was a finding. So in conclusion, analysed under EL 15978, refurbishment can outperform a similar new build over a 60-year lifespan, but requires similar operational energy performance. Existing offices can represent through refurbishment a viable alternative to demolition and rebuild. Similar levels of operational energy to new build standards are achieved. Analysis of early carbon impacts and how they impact whole life carbon in projects is important. And also just to say here, minimising initial carbon doesn't necessarily translate to minimal carbon emission over the life of the building. So if we take the refurbishment case with all the PV, it had a very high initial body carbon, but actually over the lifespan gave it less emissions. So it doesn't necessarily translate that early saving on early carbon is going to translate over the whole life cycle. The maintenance and replacement cycle is a key impact area for the office typology. Represents an opportunity to reduce emissions through examination of replacement cycles. The MEP and furniture are key contributors and must be included in studies if their influence is to be reduced. Grid decarbonisation did not change the relative outcome of the study, but as the grid decarbonises, the impact of operational carbon on LCA reduces, while the impacts from body carbon will increase. This merits further study. And there are still huge challenges to complete an LCA. We need more EPDs. So, thanks very much.